Curvature and normal vectors, part 2. Curvature of a smooth curve is the rate at which the unit tangent vector changes as we move along a curve. Curvature is non-negative and is equal to 0 when the curve is a straight line. The tighter the curve, the greater the curvature. If we want to find curvature when time is our parameter instead of arc length, we can use this formula. Let's find curvature of the helix. All right, find your velocity. Now, find speed. Lastly, find your unit tangent vector. We're not quite done, as you can see if you look at the formula. Next, we need to find the derivative of the unit tangent vector. This is what I get. Find its magnitude. I get radical 5 over 5. All right, almost done. We just need to put it all together. How about 1/10? Did you get that? Now that's a rather low number, probably due to the fact that we're going up while we're going around and around. This formula is sometimes a little bit easier to use, so let's run through the problem again using cross product this time. Same problem, different approach. We already know velocity and we already know speed. Let's find the cross product. This is what I get for my setup. And this is what I get for the cross product. And when I clean it up, it's even prettier. Find the magnitude of the cross product. Put this together with speed raised to the third power, and I get 1/10 again, which is great because if I got a different answer, I'd really be embarrassed. Curvature answers the question of how fast a curve turns. The principal unit normal vector determines the direction in which a curve turns. Arc length is sometimes a bit of a nuisance to use, and sometimes I'd rather use time. So I'm going to use the fact that speed is positive, and I'm also going to use the chain rule to come up with an alternative formula. I'd like to point out to you that the unit tangent vector points in the direction of the vector tangent to the curve, while the unit normal vector points in the direction in which a curve turns. They are orthogonal to each other. Let's find the unit normal vector for our helix. We don't need to find the unit tangent vector, we already did that. But take its derivative and find the magnitude of its derivative. This is what I get. Now I'm going to use the Pythagorean theorem to clean this up, and I get this vector for the unit normal vector. All right, notice that they are orthogonal to each other, and also notice they're each of length 1. Lastly, I'd like you to notice that the unit tangent vector is not parallel to the xy plane, while the unit normal vector is. Just kind of interesting. There are two ways to accelerate, that is to change velocity. We can either change the speed and we can change direction of motion. So speed or motion. If we're going to express acceleration this way, it's convenient to use the unit normal vector and the unit tangent vector. In that case, the the normal component is given here. Notice that it increases with speed and curvature. Here's an alternative formula that you might want to use. The tangential component is our normal acceleration if we're moving along a straight line. Have fun with this, and let me know if you have any questions as you do your homework.